and talk through the Unit 2.2 handout, Physics 167, where we're talking about the frequency and loudness response of our ears. Okay, so Roman numeral number 2 is talking about this picture, the equal loudness level contours. Okay, and so the idea here is that on this axis, we have the sound level in decibels that we've been talking about and that you calculated, from a pressure in pascals with your equation. Okay, then on this axis is the frequency in hertz. Okay, so for different frequencies and sound level combinations, how well or how loud will we perceive a certain sound? Okay, so this dashed line here is the threshold of hearing. So on average, these are the lowest sound levels in decibels that a person can hear at each frequency. So at 31 hertz, it means that we would have to have a sound of approximately 58, 59, something like that, decibels for us to be able to hear it at all. Whereas at 4,000 or at 2,000 hertz, right, something kind of like 3 or 4 decibels we would be able to hear. Okay, so that's like the lowest combination of sound level and frequency that we can hear. Okay, but those are not actually what is used on the audiogram. Okay, and we'll talk about this again when we do hearing impairment. But just remember that the pluses are what are actually used on the audiogram when you're trying to evaluate how well someone is hearing, how well they can understand speech, or if they need a hearing aid and how much you should boost hearing. Okay, that's what the pluses are. Okay, so the pluses equals the audiogram threshold. For what's called normal hearing. Okay. Now these other lines are all represent combinations of, so the equal loudness level contours all represent combinations of sound level in decibels and frequency in hertz that are perceived as being equally loud. Okay, so that means that if I have a 31 hertz tone, that's roughly 66 or 7 decibels, that's going to sound equally loud as a 62 hertz tone at roughly 48 decibels, 125 hertz tone at something like 32 decibels, 250 hertz tone at 22 decibels, a 500 hertz tone at 20 decibels, 1000 hertz tone at 20 decibels, a 2000 hertz tone at like 19 decibels, a 4000 hertz tone at like 12 decibels, 8000 hertz tone, etc. Okay, so every dot on this line, everything on that line, all frequency level combinations, sound level combinations are going to be perceived as being equally loud. Okay. All right. And those curves flatten out as the level increases. All right, so now let's go ahead and work through some of these. Okay, so number 1, what is the loudness in fawn of a 1000 hertz tone? Okay, so you find 1000 hertz tone played at 60 decibels. So you find 60 decibels and you go to where those meet right here. Okay, and then you see that it is on the 60 fawn curve. So the answer for that one is 60 fawn. That is the loudness level. Okay. Number 2 says, what is the loudness level in fawn of a 31 hertz tone played at 68 decibels? Okay, so now I'm doing 31. I need to not do orange. I already used orange, trying to be color coded here. Okay. Number 2. So 31 hertz and 68 decibels. Okay, and I'm not gonna trick you. We're always just gonna go with something that's on the line. And then you follow that line down to where you see that it is the 20 fawn line, which is A. Okay. All right. Number 3 says, what is the loudness level in fawns of an 8000 hertz tone played at 70 decibels? So I find 8000 hertz, I find 70 decibels, which is right about here, halfway between 60 and 80. And I find that that resides on, again, the 60 fawn line. So it sounds equally loud as what was in our original example. Okay, so that's 30 fawn, or 60 fawns, sorry, which is B. All right, number 4 says, what is the level in decibels? So now we're trying to find the level given a loudness level. So at 1,000 hertz, again, I'm at 1,000 hertz here, 1,000 hertz, and I go up to the 60 fawn line. So this line right here, so which is this spot right here. And now I trace it across to find 60 decibels. All right. Number 5. That's too close in color. Let me choose a more contrasting color. Let's see, what haven't I used yet? Red. Number 5. What is the level in decibels? Okay, so level equals question mark. So I'm looking for the decibels, okay, of 125 hertz tone, so here, and a 40 fawn line. So I find the 40 fawn line and I follow it over to where I hit my 125 hertz thing. And then I take that across, and that's going to be between, so halfway between would be 50, right? So it's a little more than 45 and not quite 50. So you can just kind of think of these as, you know, in quarters. I'm never going to make you guess closer than that, just estimate. Okay, so number 5 then is approximately 47 decibels, which is number C. I got the 47 by just saying it's between 45 and 50. And so it's between 45 and 50, and that's the only answer between 45 and 50 is C, 47. Okay. All right, and let's go ahead and now do number 6. Number 6 says, what is the levels of decibels? So again, I'm looking for decibels, okay, of a 4,000 hertz tone now, and 20 fawns. So I'm on the 20 fawn line. So that means I'm starting right here. Okay, and then I have to follow that over. And if you want to follow it over to this side where it's closer, that's totally fine. Or you can follow it the other way. Again, this was 20. This is 0. Halfway would be 10, right? Okay, so this is approximately 15 decibels. And then I look and see there's not a 15, but there's a 12. It's close enough. So my dot got a little big there. Anyway, so that is C. So we're just estimating. Okay, so that's how the relationship between the loudness level in fawns and the sound level. Okay, the loudness level takes into account all of that frequency dependence of our ear. Okay. All right, so now the next part, I'm just going to do a little table here. This table's in the notes and in your text. For a loudness level in fawns, what is the corresponding zones, which is the unit they use for loudness for the hearing science people, audiologists. 40, the 40 fawn curve is defined as 1 zone. Okay. And then 50 is 2, 60 is 4, 70 is 8, 80 is 16, 90 is 32, and 100 is 64. Okay. And so why zones? Well, zones is a number that doubles every time our perceived loudness doubles. And so that's why they like that mapping, that change. So I know that loudness and loudness level are hard to distinguish, so I will always say loudness level in fawns or loudness in zones to help you know what we are talking about. Okay, so using this chart here, question number 7 says, What is the loudness in tone of a 1000 hertz tone with a loudness level of 60 fons? So the first thing is to figure out what you're going for. You're going for tones. That's your question mark. What are you given? You're given 1000 hertz tone and 60 fons. So you look at 60 fon, you use the table and you see, oh, that's 4 tones. Okay. Okay. So the frequency doesn't matter if you're only doing phones to sones and fons. The frequency matters only when you're getting to the fons, between the decibels and the fons. Okay. So number 8. What is the loudness in tones? Okay, so write down tones is what I'm looking for. Of a 32 hertz tone, again, frequency doesn't matter right now. 60 fon, so I'm still at that, which means if I follow that across, I have the exact same answer there. So that would be C for 8. And then number 9, what is the loudness level in fon of 8000 hertz tone with a loudness of 2 tones? So what am I looking for now? I'm looking for fons. I'm starting with tones. I'm starting with 2 tones. And then I'm following it across and saying, oh, that's 50 fon. Again, frequency doesn't matter for this particular conversion. You're just using the table. All right, now we're going to do the multi-step where we go from tones to decibels and decibels to tones. So we'll need our chart and our table and our graph, the equal loudness level contour graph. Okay, so here we go, number 10. Okay, so number 10, I'm going to do an orange. So what is the sound level in decibels? Okay, so decibels is what I'm looking for. Okay, I have a 4000 hertz tone, and I have a loudness of 4 tones. Okay, so step number 1 is to figure out the fons from the table. So again, 4 tones. I come back up here. 4 tones corresponds to 60 fon. Okay, so 4 tones has 60 fon from the table. That's step 1. Okay, and then step 2 is to say, okay, now I'm with my equal loudness contour graphs. I find the 60 fon line. Okay. And then I follow that over to 4000 hertz. So that's step number 3. And then step number 4 is to take that over to the actual decibels. And this is 40 and this is 60. So that's 50. So it's somewhere between 50 and 55 kind of. Oh wait, did I do it right? Yes, so it's 51. Okay, so that turns into being 51 decibels, which is B. Okay, let's try to do another one here. Oh, I have one for each. Okay, so now we're going to do number 11. What is the sound level in decibels? Okay, so again, decibels was the question. Of 8000 hertz tone and 16 tones. Okay, step 1 is to find out how many fons from the table. So if I come back up to my table, I have 16 tones. Okay, it will give me 80 fon. Okay. And then I find my 80 fon line on here. That's my second step. And then I go, my frequency is 8000 hertz. So I follow along to 8000 hertz right there. And then step number 3 is I pull it across here to the axis and I say this is 80 and this is 100. So it's very close to 90. So it is C. 89 decibels. Okay, now number 12, we're going to go the other way. Number 12. Okay, so loudness in tones is the question mark this time. And we have 62 hertz tone, and we have a level of 75 decibels. Again, the FONS is the intermediate step. So step 1 is to find 75 decibels, right about there, and 62 hertz right here. And follow that across and find that. So that's step 1, is to find, and then so identify the point on the graph is step 1. Follow it over to the 60 and find out the number of FONs. Okay, so it's 60 FON. That's step number 2. Okay, and then step number 3 is to go to SONs from using the table. Okay, so if I take my 60 FON and I come back up here, I can see that 60 FONs corresponds to 4 SONs. So that's my answer, which is C. I'm going to go ahead and do one more since I have one more graph here. Well, I have multiple graphs. Anyway, just going to do one more. This is an extra one just to practice. That's going from decibels to SONs again. Okay, let's say we have a 250 hertz tone and we have 23 decibels. And we want to know the SONs, the loudness in SONs. Okay, step 1 is find the point on the graph. Right there. Step 2 is to follow it along and see that it comes to the 20 FON curve. And then look at the table. And the table in your book does have 20 FON. I didn't particularly write it down here, but from the table you will see it is 0.4 SONs. We typically won't use that low. This was just an off the top of my head example. But that table will be on your test. You don't have to remember the FONs to SONs conversion. You just need to know how to use it. Okay. For Roman numeral number 3, about the idea of a missing fundamental, I recommend that you go to the external links. There's a very fun example there that you can hear of that. All right, so Roman numeral number 4 is what we're on now here. For just noticeable differences for sound level. The idea is if you hear 2 tones, subsequent tones, how far apart do they have to be in hertz to hear their different pitches, and how far apart do they have to be in decibels for them to be perceived as being different loudnesses? Okay, so you have 2 tables that look very similar. Okay, so you have the rows correspond to the frequency that you're talking about. The columns correspond to the, roughly, are we a loud sound or a quiet sound, which decibel level we're talking about. Okay, but on this just noticeable difference for sound level, all of these elements here are in decibels. And you will notice on the level chart that they're all around 1. They're all roughly 1. Okay, and that is because in general, our ears can detect approximately a 1 dBA change. And so what that means then is, that's one of the reasons why decibels are so useful, is because we can't really detect individual, like the teeny changes in pressure in pascals, but it's about 1 decibel. Okay. All right. So let's do these. Let me explain the other chart now. I'll use purple for this one. So again, this column here is the frequency. So you find which frequency we're talking about. And then you find, the row is the frequency. And then this, which column is basically like, are we at, almost can't hear? Or are we at whisper level? Or are we at loud sound level? And it changes. So the elements in this chart here are in units of hertz. And you'll notice if you take any one of these columns and come down, there's a large increase in the number of hertz as the frequency goes up. Now, another thing to notice is that these are double, like 2 times 200 is 400. 400 times 2 is 800. 800 times 2 is 1600. Anyway, so basically, when you double the frequency, it's like an octave. That's not important now, but we'll come back to it later. All right, so now we're going to do some examples. Okay, number 13. Can you hear a difference between a 2000 hertz tone at 40 decibels and a 2000 hertz tone at 39 decibels? So first question is, which table am I going to use? And you're going to use the table that corresponds to what is different. Okay, so in this case, levels are different. So we're going to use the just noticeable differences for levels. Okay. And then you come to your table, you find the 2000 hertz row, you find the 40 dB column, you say 1.17. I will perceive those as different sound levels if there's at least 1.17 dB difference. And then you take the difference between what's given in your problem, 40 minus 39 is 1 decibels, and then you compare that difference to what's in your table. So 1 dB is less than the 1.17 dB from the table. That means they will not be perceived as different. Okay, so for it to be perceived as different, it has to be greater than or equal to what's on the table. All right, now let's do number 14. Number 14 says we have a 1000 hertz tone at 20 decibels and a 1000 hertz tone at 21.5 decibels. Okay. And so you come to your chart and you say, okay, I have 1000 hertz, I'm around 20 decibels. That means 1.37 is my J and D. Okay, so J and D is equal to 1.37. And the difference between what I'm given, the two sounds I'm considering, 21.5 and 20, is 1.5 dB, okay? And then you're comparing the difference to the just noticeable difference. And in this case, the difference is greater than the just noticeable difference. So that means that, yes, they will be perceived as different. So just to be consistent over here, this is the difference between what you're listening to, and this is the just noticeable difference. So if the just noticeable difference, if the difference is less than the just noticeable difference, then you will not hear it. If it's greater, you will hear it. Okay, number 15. Sorry, that was number 14. Okay, can you hear a difference between a 4000 hertz tone at 40 decibels and a 4010 hertz tone at 40 decibels? Okay, so now which table? Okay, we're going to be using just noticeable differences for frequency because it's the frequency that's different. Okay, all right. So I have to go to my 4000 hertz row and then the 40 dB column, find my element, the J and D for frequency at 4000 hertz and 40 dBs, 40 decibels is 15.9 hertz. And then the difference between my two frequencies are 4000 and 4010 minus 4000. You just always want to do bigger minus smaller to get a positive number. I'm just going to be considering positive numbers. So that is a 10 hertz difference. Okay, 10 hertz is less than 15.9 hertz. And if the difference is less than the just noticeable difference, then the answer is no, they will not be perceived as different. Okay, and then number 16 says, can you hear a difference between a 600 hertz tone at 40 decibels and a 597 hertz tone at 40 decibels? Okay, so again, you're going to come here to the 600 hertz row, the 40 decibel column. That's the element you're looking at. The just noticeable difference is equal to 1.1. But the difference between the frequencies we're interested in is 600 minus 597 hertz, or 3 hertz. So the difference is greater than the just noticeable difference. So that means, yes, they are perceived as different. So again, these just noticeable differences can be a plus or a minus. So like here, the frequency was lower by 3 hertz, right? And here it was higher. So these can be either, you just take whatever you're at and you can do add or subtract, just noticeable differences to find out what will be perceived as different. Okay, hopefully that is helpful. Good luck.